even though matching has been studied so extensively and there are so many, from so many facets and so many very important results, there are some very important questions still open about matching. One of them is approximately count the number of matchings in perfect matchings in a non-bipartite graph. In bipartite, you can do it through Jerome Sinclair Bigota. And the other is matching in deterministic NC. So I would say these two are probably the two of the handful of outstanding big open problems in exact algorithms. So, yeah, let's go to part 2, where I'll describe the MV algorithm. And as I said, I will give you all the graph theoretic definitions and show how that leads to a proof of this algorithm, and also talk about the question that was asked, I think by you, I don't know who, about the synchronization, which is coming up in a moment. So the MV algorithm runs in phases. In a phase, a maximal set of disjoint minimum length augmenting paths with respect to the current matching M is found, and it should be found in order M time, which means that we do constant amount of work per edge, and then we are allowed to use some data structures actually we'll need, and but it turns out that can be also subsumed in order M time. So again, recalling the even level and odd level of a vertex is the length of the minimum even and odd length alternating path from an unmatched vertex, whichever gives it the minimum, to V, infinity if none. And min level and max level are the smaller and the larger of even level and odd level. And as in the bipartite case, we will search simultaneously from all unmatched vertices. But in the examples, I will typically have only one unmatched vertex to illustrate everything, almost, unless I have to show you an augmenting path. So again, a prop, an edge is a prop. If one endpoint is a predecessor of other, that means this gives, if U gives V, its min level, minimum level, the smaller of even level and odd level. And an edge is a bridge if it is not a prop, and a bridge assigns max levels, like we saw. And I'm going to show it again. So in this graph, this is the unique bridge. All the other edges are props, and the props give min levels to all these vertices, and the bridge gives max levels to these 4 vertices, the 5s and the 6s, right? And I'm going to talk about this triangle that I put up last time, at the end of the last talk, that I'm going to define. So I've defined bridge completely graph theoretically, right? Because prop has been defined graph theoretically. It's something that gives a min level. The last edge should be the last, the edge, this edge should be the last edge on a min level path. Whenever that happens, then this edge is a prop. And if an edge is not a prop, it's a bridge by definition. Not every bridge gives max levels to something, and we'll see why. Okay, so tenacity has been defined for vertices. It will also be defined for edges, and this is a central notion, these two, that hold together these 3 important concepts of bridge, blossom, and base, which have to be completely graph theoretically defined. And you may ask, why graph theoretically? Because it's so much harder, and I'll give a justification for that also. Okay, so this I already defined. Tenacity of a vertex is the sum of the even level and odd level by definition. And here, these 4 vertices in this blossom have finite tenacity, namely 6 plus 3, 5 plus 4, and so on. And like I said in the last talk, that if you take an odd level path to this vertex and an even level path to this vertex and concatenate them, you'll get some kind of a lollipop. And that lollipop is the same lollipop you get for each of these vertices. And that's why they have the same tenacity. And so these 4 have 13 tenacity, these purples have 15 tenacity, and the yellows have 17 tenacity. And now I'm going to define the tenacity of an edge. So again, it's a question of enclosing the edge in a lollipop. Okay, so if the edge is unmatched, then you would like to come to its two endpoints with even level paths. To get an alternate, the lollipop has to be alternating. So these are the two endpoints of this edge. You want to come with an even length path here and an even length path, and concatenate those two paths together with that edge. That's the lollipop that defines the tenacity of this edge, or any edge. And so the tenacity of an edge is defined to be the following. If UV is unmatched, then it's the even level of U plus the even level of V plus 1. 1 for the edge itself. And if it's a matched edge, then it's the odd level of U plus the odd level of V plus 1. Right? Is that okay? Again, feel free to ask any number of questions. Aaron, you always have a question. Not yet. Okay. So these are tenacity 9 edges, right? For example, what's the tenacity of this edge? It's the even level of this plus the even level of this plus 1. So it's the same lollipop that gives it its tenacity, even though this vertex is not of finite tenacity. Because its odd level is infinity.
Sorry, I forgot it earlier.
Yeah.
I saw that the tenacity is associated with a node, not with an edge.
Both. I already defined the tenacity of a node this way. Of an edge, it's defined in two ways, depending on whether the edge is unmatched or matched. And it's always trying to put that edge in an alternating lollipop. Okay, so and that's what will do it. Because if you come here with an even length path, take this edge and go back with an even length path, you'll get an alternating lollipop. If you come here with an odd length path, take this matched edge and go back with an odd length path, you'll get an alternating lollipop. That's what it is. So these are tenacity 9 edges, the green ones. And here, these edges green are tenacity 13, the purple are tenacity 15, and the yellow are tenacity 17. And I've also marked the vertices with their tenacities, the colors, right? So these are like absolutely the key notions. Everything else big sits on that. Okay, so right away, let's talking about the algorithm. Two main ideas: double depth first search, which I showed in the last lecture, and a precise synchronization of events. And that means a lot of things. And I'll say slowly what all it means. So half this talk is about this aspect. This is already done. This aspect, and the other half is about how to get these graph theoretic definitions and prove the algorithm correct, and why graph theory is needed, graph theoretic invariance rather than algorithmically defined notions. So here's an outline of the algorithm, the main routine, which is an intertwined breadth first search with double depth first searches. And that's a mouthful, so let's tear away some part of it. And I'm just going to look at this top part, which assigns min levels in the non-bipartite case. But actually, this is the same thing that we did in the bipartite case when we were looking for shortest augmenting paths in a bipartite graph. Remember, we were searching with search level I from 0, looking at unmatched edges, then matched edges, then unmatched edges, and giving a level of I plus 1 each time when we found new vertices. This is exactly what we did in the bipartite case. So this remains here. This remains within the non-bipartite case, but just to assign min levels. Okay. But we also have to assign max levels, and that involves running double depth first search on bridges of tenacity at search level I. This is the precise synchronization of events. At search level I, run double depth first search on every bridge of tenacity 2i plus 1 to find all vertices of tenacity 2i plus 1. Whether or not we'll find all vertices, whether we'll know what all bridges are, those are questions still to be answered, right? But this outline is okay. And when I say search from all vertices of level I mean that if I is odd, these are vertices with odd level I. If I is even, then these are vertices with even level I. And whether you search along the unmatched edge or the matched edge depends on all. The parity has to be correct. And that's the same as bipartite case in this out here. Okay, so here, this is the bridge of tenacity 9. So if I want to find at what search level will we do double depth search on this? At search level 4, because 2 times 4 plus 1 is 9. And at search level 4, we find this bridge, we find its tenacity, and then we do double depth search to find these other vertices and give them their max levels. Okay. And the max level will always be 2i plus 1 minus the min level, because the tenacity, these vertices that we encounter will all be of tenacity 2i plus 1. We know their min level, so we can subtract and get their max levels. But are we sure we'll find, when we hit a vertex, are we sure it's of tenacity 2i plus 1 and not less or more? That's the big question. So the question is, what does it take to prove this kind of a scheme? And the answer has to be induction, that if you did everything correctly up to search level I, then on search level I plus 1, also you'll do things correctly. And what does it correctly mean? Well, for min, it's very easy to see that this scheme works, because the agent that assigns min level to a vertex is one of its neighbors, namely a predecessor, right? And the predecessor must have a level of I if it's assigning a level of I plus 1 to this. I'm not talking about parities. Parities take care of themselves, even, odd, and all that, right? So you must have a level of I. And has a level of I been assigned to you? Well, if I is the min level of you, yes, because of the way the min is structured. What if I is the max level of V? In that case, the min level of U is only less than I minus 1 or less. So its tenacity is 2i minus 1. So it has been assigned a max level also in the previous search level, in the max of the previous search level. So if everything happened correctly up to search level I minus 1, if we follow this recipe, and we can prove that we followed it to the dot, then everything will be done correctly in this search level also, as far as min is concerned. Okay. But what about max? So for the case of max, the max level is given by a bridge, sort of given by a bridge, which is far away from the vertex. It could be arbitrarily far away, because it could be a very long, skinny blossom, right? And so the following questions arise. Is there such a bridge which will assign V its max level? And what does such mean? We have to define that, right? And will it be found at the correct time so that max is assigned, this V gets its max level, right? These are the natural questions that arise. Sushant, you have a question?
No, I'm trying to parse the max.
The max? Yeah.
Like the max process. Data science.
These are clearly the two questions. Huh?
And also, we are currently not diving into how the running time complexity yet, right? Because
of course, that will be the main story, but for now, yeah.
For now, just making sure.
Yeah. Are we okay with these two basic questions? We have to answer these, right? Otherwise, we cannot even give a proof through induction. So, and again, we come back to these, and so I was thought of saying that the blossom is defined through the bridge, and I was saying it's an approximate way of looking at things just to get things going. And the real story is that a blossom is a function of what? Tenacity and base. And I have to define the base of a vertex. This is also a graph theoretic definition of base of a vertex, not algorithmic. Okay? How do we define the base of a vertex? And that is needed to define a blossom. So, and this is a mouthful. This definition takes a fair amount of things to get to it. So let's take it softly and first start talking about the significance of base. Okay, if this is a vertex, then that's its base. And what's happening with this base? The base is present on every even level V and odd level V path, on every one of them. At least in this simple case, you can see that odd level V and even level V, and the base is always present. And this is always true. Okay. And the tenacity of base is strictly more than the tenacity of the vertex. This is also a fact. Here, tenacity of this vertex is infinity because its odd level is infinity. There's no odd path from F to this guy, right? And this is also a fact. So here is sort of a starting definition, and we will add more body to it in a moment. And I don't want to start with all the paraphernalia and then come to the main. I want to come to the main point and then add the extra stuff around it slowly. So what's the base of a vertex? Say that this vertex is of tenacity T, and let P be an even level or odd level V path starting at unmatched vertex F, let's say, and assume that the tenacity of this vertex is strictly smaller than the tenacity of F. Okay. Unmatched vertices have the highest tenacity, and the tenacity of an unmatched vertex is either infinity or is the length of the shortest augmenting path, including that unmatched vertex. And if you look at all unmatched vertices and look at the one that has the smallest tenacity, that's the length of the minimum augmenting path, obviously, right? Right? So for this path, I'm going to define the base of V. Yeah.
So an unmatched vertex, even it could just have a min level and the max level could be infinity, right?
It could be infinity.
Do we say that tenacity is infinity, or do we say it's the?
Of course, tenacity is infinity. It's even plus odd.
But we want to find this small.
But I'm saying tenacity of V is smaller than this. The tenacity of V is finite. Whose base we want is. But okay, if you hold on you'll get a very precise answer to your question when I complete the picture, because I'm going to the center of the picture, and then when I put the periphery stuff around it, it'll become complete. So take this path, even level or odd level, and let BVP be the highest vertex on this path. So look at the path going from F to V, and F is, of course, of tenacity strictly bigger than T. Now look at the tenacities of all the vertices on this path. Are they smaller than T or bigger than T or equal to T? Now, the ones that are bigger than T, find the one that's highest on this path and call that BVP. Okay, so on this path, the highest vertex of strictly higher tenacity than T. And then look at all possible even level and odd level V paths, T, and look at this entire set of BVPs over all such paths. How big do you think that set is? You see what I'm doing? Sorry? It's one. So I'm looking at V and looking at an even length path, and then looking at an odd. Suppose odd level is bigger than even level, and all these paths. So all of the odd level paths will be of the same length. I'm just drawing them. They share edges, of course, and here they are. And each time I'm putting a cross on the highest vertex of tenacity strictly bigger than T, bigger than T, bigger than T. Of course, F is bigger than T, but that may not be the highest vertex of tenacity bigger than T. Okay, and I'm collecting all of these vertices, highest vertex of tenacity bigger than T, and I'm forming that set. And I want to claim that that set is a singleton, like you said. Why do you think it's a singleton?
That I think is going to be, that's what you're looking for, right? That's going to be the base, right?
Right. So this BVP is independent of P. There's only one such vertex, and that will be called the base, say B. So that's a graph theoretic fact. Okay. Towards the end of the talk, I'll give you a challenge to prove this theorem by itself. I don't see how to prove this theorem by itself, standalone. I only know how to prove this theorem along with 5 other theorems through a very massive induction that uses all the facts together all at once and keeps building through induction all the assertions. Okay. But we'll come to that. Any questions? So okay. And so this is called the base. And B is called a basal vertex. These are special vertices, which will be the bases of blossoms. Okay, and of course, the tenacity of the base by definition is strictly bigger because these are of tenacity strictly bigger than T. Okay, clear? Okay. So let me finally get this assumption out that tenacity of T is strictly smaller than tenacity of F. What is tenacity of F? Can we allow infinity tenacity in F? Okay, so I don't know that I should get here. I'll come back to these. So to come to the periphery that I was talking about, I need to show you that a vertex of tenacity, so LM is the length of a minimum length augmenting path. So by definition, it is take all unmatched vertices, look at their tenacities, and take the min of these. That is the length of the minimum length augmenting path, right? If you take all unmatched vertices, look at their tenacities, and sort them by tenacity, and take the smallest one, that's the length of the shortest augmenting path. I'm calling that length LM. And I'm asking this question: if a vertex is of tenacity LM, does it have to have a base? And the answer is no. For instance, in this graph, all the vertices have tenacity 3, which is LM, and the tenacity of the base has to be strictly higher, right? But remember, what's the purpose of the base? It is present on all even level and odd level paths to the vertex. And why doesn't this vertex serve that purpose? Because it is on the odd level path and the even level path. So why don't we call this the base of V, even though its tenacity is the same as the tenacity of V? Well, this picture is a bit deceptive because as soon as I add this edge, which doesn't change the tenacity of any vertex, I get an odd level path from here, odd level path from here, even level path from here, even level path from here, and even level path from here. So this cannot be the base, even by any other definition, right? So this is a boundary case, and now I need to define the notion of eligible tenacity. So LM is the length of a minimum augmenting path. TM is the tenacity of a minimum tenacity vertex. Among all tenacities, there must be a minimum. Look at that. And an odd number which lies between TM and strictly less than LM is called eligible tenacity. And vertices of eligible tenacity have bases and are precisely the set of vertices which will be in blossoms that are defined from the point of view of minimum length alternating paths. So once I define blossoms, you'll see that these vertices of eligible tenacity. So if I had to define base again, full force, I would define eligible tenacity, then take a vertex of eligible tenacity and go through these motions to define the base. So it's defined only for vertices of eligible tenacity. And once base is defined, this is what it gives. It allows us, okay, we won't do this divide and conquer because we have no time to waste around on even divide and conquer. But basically, if we found any shortest even length path from F to the base, and a shortest path from base to V of either parity starting with an unmatched edge, then they will be meeting only at B. So in other words, this shortest path from B to V starting with an unmatched edge cannot hit this stem. It meets this stem only at B, and so you could have found this path and that path independently and stuck them together. You would get an even level path or an odd level path. So the base is some sense allows you to do divide and conquer, though we will not use this fact. Conceptually, this is true, and this is an important theorem for the structure that I'm talking about, but it's not for an algorithm. Okay, so basically, this vertex has this base because every even level V and odd level P path goes through this vertex. This is a purple vertex. It has higher tenacity than green. The purple vertices have this as base, and it's a vertex of tenacity yellow, which is higher. And so this is the base square of V. and that's the base cube of V. And these are called the iterated bases of the vertex. And this will be an important notion later. It'll come about towards the end. I'll bring it back. So we already answered this question. So remember, we defined outer and inner algorithmically for Edmonds' algorithm. Here we can define it graph theoretically. So a vertex is outer if its even level is smaller than odd level, and inner otherwise. And a basal vertex is always outer. So its even level is smaller than its odd level, which is here infinity. So this base, and this base are all outer vertices. Their even level is smaller than the odd level. And the blossom, again, has two functions, just like Edmonds. In Edmonds, it gives the other level, right, to make inner vertices outer. And here it gives max levels. And it hides complexity. In the case of Edmonds, it contains the shortest even length path, either going clockwise or anti-clockwise. And to the outside world, it looks that macro node looks just like a node. Here also, Blossom hides complexity because it contains all shortest paths from B to vertices in the Blossom. Shortest paths, just like I had said earlier, right? So this is similar to Edmonds, but there are two differences. One, of course, is this is a definition from the viewpoint of minimum length. And two, what I'm going to define in the next slide is a Blossom from a purely graph theoretic perspective, not an algorithmic perspective like Edmonds. So it'll be a mouthful, so please be ready. So here's a recursive definition of a Blossom. So let B be an outer vertex whose tenacity is bigger than T, where T is some odd number of eligible tenacity. And the Blossom with base B and tenacity T is the following set. If T is 1, it's an empty set. Assume that blossoms of tenacity T minus 1 or 2 are already defined, smaller tenacity. And let S be those vertices which have tenacity T and whose base is B. Right? We know what it means to say that a base of a vertex is B. Then the Blossom with base B and tenacity T is all these vertices and all the smaller blossoms sitting at these vertices. Smaller, by smaller, I mean of tenacity T minus 2. Okay. Alistair, are you happy with that? This might be important, right? Sorry?
Sure.
Yeah, okay. So here, what is the Blossom of tenacity green with this base? It's the 4 green vertices, right? What's the Blossom of tenacity purple, which means 15, with this base? It's the purple vertices plus this sub-blossom, because it's a sub-blossom sitting on this purple vertex. What's the Blossom of tenacity green on this base? Huh? Sorry?
Is it empty set?
Empty set, because no green vertex has this as a base. What's the Blossom of tenacity yellow with this base? It's a yellow, purple, and green. So that defines blossoms, that defines nesting of blossoms. One blossom is nested in the other if it's a subset. And the point is that a bridge does not define a blossom. So for instance, here we have 2 bridges of tenacity 11, and this whole thing is a blossom other than this unmatched vertex. This whole thing is one blossom. Okay. B with tenacity 11. So the blossom of base B and tenacity green is this. Base B and tenacity purple is the whole thing. Same here. So there's very little difference between these two, even though they look quite different. Blossom of tenacity green and this base is just these two. Tenacity green and tenacity purple and base B is all 4. Because this is sitting on the base, and then these are the base of these purple vertices is this guy, far away. There's no purple vertex on the way. It doesn't have to be. Do you see what's happening here? Something very funny, very strange. because this vertex is predecessor of this is predecessor of this is predecessor of this is predecessor of this, right? These are giving min levels. So this vertex is predecessor star, if that's the recursive definition, predecessor star of this, and yet this is not a predecessor, not a prop. This is the bridge of tenacity 13. And so in this case, we have a blossom with this base and tenacity 7, and blossom with this base, and tenacity 13 is all these vertices. Question, Aviv?
So these graphs are, these pictures are done by.
Yeah, min level, yes, always min level.
Maybe why are there two unmatched edges next to each other that go from one level to the next up there?
But this is the alternating part.
Okay. I'll have to think about it.
Yeah.
So, this is.
Okay, so blossoms are well behaved in that sense that they form a laminar family. Blossoms hide complexity just like Edmonds, but we can state it very formally. Basically, I don't want to do that because you already know what I'm about to say here. And then 3 tasks which have to be done in order, a constant time per edge plus some data structure work. Okay, so first is forward search, which is alternating breadth first search plus double depth first search to mark predecessors and blossoms and assign even and odd levels. And then once you find augmenting path, to find that, what does it take? And then to erase judiciously if there's no augmenting path. Okay. So marking blossoms so paths can be found quickly. So what does it take to? So eventually, when we find a blossom, we'll have to find a path through it. Again, we are allowed only constant amount of work per edge. Okay, so if we go through a blossom again and again, the same edge again and again, that's not allowed. Each edge can be looked at only a constant number of times. So let's see what it takes. So at search level 4, we'll find that black edge and mark it 5, 5, and this black edge will also be found because from here we search along this edge, from here also this edge, and that's a bridge. Okay, and so it indicates that there's a blossom, and that's the blossom node that's put here when you do double depth first search and find this base, and it points to the base, and all the vertices of the blossom point to this node, and this node points to the 2 peaks, the red peak and the blue peak. Remember, there was a red tree and a blue tree in the double depth first search, and the trees were rooted at the endpoints of the bridge. That's why we are pointing to here, because when we need to find a path through the blossom, we need to come to the root of this and find a path in this red tree or the blue tree appropriately. And then what happens at search level 5? We find this edge, which is a bridge, and that creates another blossom. And this node is part of that blossom. This is the base of the small blossom, but it belongs to the big blossom, and so on. Okay, so and then again, there's a distinction between graph theoretic and algorithmic notion. Yeah.
So when we have nested blossoms, we don't add pointers to the higher level blossoms for, let's say, the node number.
From the base to the.
But not say to the node number 2.
No, we will jump inside. We don't add one. Yeah, you cannot even add too many nodes in that same time. So again, there are algorithmic notions and graph theoretic notions, and the algorithm notion here is that of a petal and a bud. So these two bridges can be, you can do a depth first search on this in an arbitrary order. Say we do this, then we'll create a petal node here, and then we'll create a petal node here, and this will be a bud, and the bud star will be the base, and the union of the petals will be the blossom, as it should be, right? In any flower. Okay, so I said, what will this scheme work? Will max assign max level? Okay. So I said, what is the agent that assigns max level? It's far away. And there were these 2 questions. Oops, sorry, what is this? I'm standing right here. That's the reason. And these two questions come up. For this vertex to get its max level, there's a certain bridge that gives it its max level. What is such a bridge? And will it be found on time? What does it mean, such a bridge? Okay, so for this purpose, let me define the support of a bridge. Let UV be a bridge of tenacity T, then its support is all vertices of tenacity T, such that there's a max level path to that vertex containing this edge. Okay. So what is the support of this? There are three bridges here: green, purple, and yellow. What's the support of this? All vertices such that there's a max level path to them, which contain all vertices of tenacity green, which are such that there's a max level path containing this bridge. So there's a max level path containing this bridge, like this, like this. So these four are the support of the green bridge. The purple vertices are the support of the purple bridge, and the yellow vertices are the support of the yellow bridge. Aviv, you have a question?
It's still the other thing that.
Which one? Which one?
The one where in one of the pictures, so in this picture, when you go up a level, if you just keep going up levels, you're on an alternating path, right?
Right, always.
And then in one of the other pictures, it looked like you were going up a level.
Yeah, but because you were
In that picture, you had two black edges like this, and I was confused what was different.
Yeah, you're right. It might not be exactly at min level there. You're right. There's a reason to stretch out some edges.
I see. So
Yeah.
that one, they're
Yeah.
not arranged by mid-level.
They're not. They are arranged by min level, but the min levels have to be pulled apart.
Oh,
Yeah. Thank you. Right.
there we go.
Okay. So now this edge is not a prop, right? These vertices get their min levels from somewhere else. It's not a prop. It's a bridge. What's the support of this bridge? Nothing, because it doesn't give. It's not on a max level path to anything, or this bridge. Its support is empty. But you would not know that its support is empty until you do double defer search on it and arrive at the bottom here without finding anything new. So here's why graph theory is needed. So let V be a vertex of tenacity T. Then we have to show that V is in the support of a bridge of tenacity T. Right? So let V be a vertex of tenacity T and P be a max level path to V. Then this theorem says that there is a unique bridge of tenacity T on P. So that if you did double defer search on that bridge, you will reach V. And therefore, every vertex of tenacity T has a bridge that will give it its max level. That's what was needed to show, that every vertex of which has a certain max level, there's a certain bridge that will always give it that max level, and that's the one that sits on the max level path. And this is a purely graph theoretic fact. There's no algorithmic fact here. This is a graph theoretic fact. You have to prove it graph theoretically. And this is like one of the last facts that needs to be proven after. It can be proven only after you know base, blossom, bridge, and everything, and tenacities. Okay, so that was the question to the first answer to the first question. Does such a bridge even exist? What does it mean, such a bridge? But will it be found in time? And that comes to this question of synchronization of events. And here I have a lot of ideas to show, and depends on how much energy everybody has. Sushant, you have tons of energy?
So intuitively, the two highest vertices will form the bridge.
Yeah.
That will find the vertex of this.
Yeah. But will you find that bridge on time? Will you find this vertex on time? Will the synchronization will work out the way it was given here? Namely, at search level I, will you find every bridge of tenacity 2i plus 1? Will you find all vertices of tenacity 2i plus 1? These are big shot theorems, right? They're not trivial facts to prove. How do we prove those things?
And different paths will give rise to different bridges. So depending on which order and which order you
Always tenacity. You always process bridges by tenacity.
Right, but you said once you pick a max level path,
Yeah.
then you get a bridge, a unique bridge.
On every max level path, there is a bridge, but the bridge, that was just to show existence.
Right.
That was just to show existence. Aaron, are we fine?
I was thinking.
Yeah. So, depends on how much depth we want. I can go deeper and deeper and deeper and deeper. So, basically, remember this edge from high to low was useless in bipartite because this path will be longer than the minimum length path, right? And I said that in MV, these edges that go from high to low will be useful. Why? Well, look at this. This goes from high to low. Is it useful? It doesn't seem useful right now. Why should it be part of a minimum length alternating path? Right? If I can go like this, I can equally go like this. Well, because there may be more things here, like this. Okay, and so this edge is the only way to come around to these guys here with max level paths. How do you get to a max level here? You have to, sorry, excuse me. This bridge is the only way to come to a max level path to these guys, or to these guys. To these guys, because you come around like this. So it's not useless at all. Very useful. Right? This is the alternating path that gives max levels to these guys. And this is the alternating path that gives the max levels to these guys. And it uses this bridge, which goes from high level to low level, which was useless in the bipartite case. And this kind of bridge is special. I'm going to call it an anomaly bridge, because when you find it, its tenacity is not known, because the even level of this vertex is not known. Because the tenacity of this bridge is the even level of this plus even level of this plus 1. The even level of this vertex is not known. And whether it will get a finite even level later, nobody knows, and depends also on how big a blossom it gets put in. It could be an arbitrarily long blossom, giving it an arbitrarily large tenacity. We'll get to know about it in the future sometime. So that's why it's called an anomaly bridge. Okay. Okay, and then there's this entire question of synchronization, which is many different ideas. I don't want to go into it unless there is still horsepower left somewhere. I have, but
Yeah, we have about 25 more minutes.
we don't need more. But do we have half horsepower for 25 minutes? Because I've already done one talk. So, how many people are interested in knowing this fact? This bridge is of tenacity 11. Why? Because that becomes clear when we shrink this blossom, or not shrink, but find this blossom, because it gives an even level of 8 to this. So this bridge has tenacity 11, 4 plus 8 plus 1, which is 11, right? And so right?
13.
Oh, 13. 13. Yes. But it's the bridge of tenacity 11 which will reveal its tenacity, right? Good. So you're on with this, right? Good. That now I'm more confident about moving forward. Because even yeah. Okay. So it's of tenacity 13, as you said. The question is, we will find its tenacity at search level 5 when we find this blossom. And so the algorithm says that double depth first search on it should be done at search level 6, because that's 13 minus 1 over 2. And if we do that, we will assign these max levels to these guys. But the question is, we found its tenacity at search level 5. Why don't we do double depth first search at search level 5 itself? Okay. In other words, break the rules of synchrony that were laid out. What will go wrong? I'll also show you exactly what will go wrong. Okay, is that okay? So here's what will go wrong. So let's see a slightly bigger example. So the search this bridge of tenacity 11 is found and processed at search level 5, and it assigns an even level of 8 here, and this bridge gets its tenacity of 15. It is not an anomaly, because at that moment it's found, its tenacity is known. You don't have to wait for the future, even though it's going from high to low. The question is, can we process it at search level 6 rather than at search level 15 minus 1 over 2, which should be 7? What goes wrong if we process it at search level 6? The following goes wrong. So at search, the following goes wrong. Because if we process it at search level 6, okay, and process this bridge before this bridge, which should also be processed at search level 6 because it's 13 minus 1 over 2, it will give tenacities of 15 to these two vertices, which is wrong. Because these two vertices actually should be getting their tenacity from this bridge and should be getting a tenacity of 13. So what went wrong? Why was it? I mean, we could have done double defer search on this, and if we came down here and labeled it 15, that was wrong. What about synchrony is it that is making it work? The point is that at search level 7, so when we do double defer search on this, there's a certain prerequisite. All lower tenacity vertices should already be in blossoms, because when we reach a vertex, we should be sure that it should get this tenacity and not a lower one, because we don't have to have time to look around and see, oh, can it get a lower tenacity? And if you have found lower tenacity vertices already and they are already in blossoms, then when you come here, you'll skip down to the base of that blossom right away and not give tenacity 15 to these guys. That's what is the, and the whole point is that you have only constant time available per edge. And so when you reach a vertex and give it a certain tenacity, you should be sure that it shouldn't be deserving a lower tenacity through some other bridge. Okay, and that's what precise synchronization of events is. Okay, then I'm almost done. Basically, suppose you come down here and you have this structure already. There's this blossom, and this contains both. This is a bigger blossom which contains both of these smaller blossoms. So there are blossom nodes here, and you jump, like you keep jumping blossoms to come to the lowest base at the moment possible. Who's going to pay for all this work? If you keep coming over and over again here, you find bigger and bigger blossoms up there, and you keep coming down these pointers, who's going to pay for all that work? So here we need data structures, because this is union find, basically. And either you can use the pointer model and incur an alpha factor more, or you can use a result of Gabor and Tarjan showing that in a RAM model itself, all of this can be done in linear time by using the RAM as a table lookup. Or you can try to prove a fact that is claimed in our paper but never proven, that if you happen to do this much work, more than linear work, then you have that many more edges to charge that work to. Because if you did all of that work, the graph has to have more. It cannot be a tiny, sparse graph. It has to have more edges, and all of that can be charged there. That's an obviosity that there should be those edges, but who can prove it? I don't have the energy or the desire to prove that, having spent 40 years on this already. So Gabor and Tarjan will suffice for this. Okay, so we have these three paths, and finding the path is easy. You jump to the endpoints of the bridge and find paths like that by following the blue tree and the red tree. And the last thing is you have to judiciously erase. That means you have to erase the path and then keep erasing vertices that don't have predecessors. Okay, and the following question comes up. After you do all this erasing, how do you know that there won't be a half-eaten blossom left? So you ate up some part of a blossom, some part still remains, and because it's not a complete blossom, no guarantees on what paths it can be part of. How are we going to find paths through this half-eaten blossom? Okay. And here more structural properties come in, namely the base is a predecessor of of all vertices in the blossom. So if base goes, the entire blossom goes. Furthermore, these iterated bases occur on every minimum length path, even level as well as odd level. So since the iterated bases occur, the biggest blossom goes away. So once you do the topological arrays, there are no half-eaten blossoms left. So once you do the arrays, you're back to the same kind of properties as to when the first path was found. So you can go back and find the next path and the next path, erase, next path, erase, next path, and be done. Okay, so the question is, why did the proof take so long? Right, that's the obvious question. And so, as if you saw the structure, to define a blossom, you first need to define a base. But to define a base, you need to show that this set of bases is a singleton. But to show it this is a singleton, you have to go back to smaller blossoms of smaller tenacity and its properties. Okay, and so there's a big chicken and egg problem here. And in fact, this theorem, which I said that BVP is independent of P and that this set is a singleton, I challenge you to prove this statement by itself. No, I don't see that it can be proven by itself. The only way it can be proven is to prove all of these facts and all the other facts all at once through an induction on tenacity. Okay, so in the induction step, you prove all the facts about the next higher tenacity, and so on. And even that's not enough in terms of ideas. Why? Because graph theory is very, very complicated. Everybody knows that. And if you want to trace single paths and start talking about this fact that this set is a singleton and start talking about all these paths and with their arbitrary intersections, it's a big spaghetti that can never be unraveled. And the big idea that came finally in recent years was to use the power of double depth for search for arguing about these things instead of arguing about individual paths. Because double depth for search gives me very specific properties about the bottlenecks. And moreover, double depth for search can be made to work on simple graphs, layered graphs that are derived from G. And once the facts are proven on that simple layered graphs, they can be ported back to the original graph. Okay, so that's what it took. I mean, this idea may have never come, except that I was giving so many talks about this that I had to break down double depth for search into its lowest elements. And once I did that, I saw that it could actually be used for a proof, not just the algorithm. And that's counterintuitive, right? Why should double depth for search, which is a graph search method, be useful for a proof? It should be used in the algorithm, but it's the central thing in both. And so this is the main algorithm, of course. And then there are pieces of it, marking up blossoms, finding paths through those blossoms by jumping to the bridges and erasing appropriately. Those are all easy pieces. And I claim that this is also very simple. And that's the whole point, that the algorithm is so simple, but the structure is so complex. I haven't even started drawing the complex things yet. But you can imagine when you put on many, many more edges, how complicated these blossoms could be. So folks here have improved the running time of flow and bipartite matching to almost linear time. But general graph matching still remains at the same 43-year-old bound. And who knows if it will ever be improved. Here's a nice blossom for you for paying attention. Thank you.
So we have time for a few questions. Any question?
Yeah.
So thank you, Vijay, for a very nice introduction and sort of a good overview of this proof. So maybe because we didn't go into, I mean, this is the first time I'm seeing double depth first search. So is it possible for you to give us an abstract view of what properties double depth first search provides in terms of a labeling or these bottleneck nodes that's
a good
useful
question.
for the structure of the algorithm?
So in the paper, I call it a double depth first search, DDFS guarantee. Just look at that. I had flashed up a slide, but it'll take a while to go back to that slide. But DDFS, at the end of it, gives you a DDFS guarantee. Namely, you have two endpoints, right, of the bridge. And you have a red tree and a green tree. And it says that if you take any vertex in the red tree, then there's a path which you can find by going to the red root, and doing search in that red tree. You'll find this vertex, and a completely disjoint path, obviously, from the blue tree root in the blue tree. And because this is a red path and this is a blue path, they are disjoint. And that's what you want, two disjoint paths, one going into the vertex itself, one going to the base. Or in case you have an augmentation, then two disjoint paths, one red path and one blue path. That's the DDFS guarantee, period. And the DDFS guarantee is that it'll find the lowest base. Okay, base of base of base of, I mean, the bud of bud of bud of bud, right? And that latter one is what is used in the proofs. If you start using individual paths, it's impossible. And that challenge that I gave you, I really mean it. I simply don't see how to do that without, yeah. Thank you. Yeah, a nice question though. And as you said, you are, despite being in this area full force, this is the first time you're seeing double depth first search, which is a travesty because it's such a powerful, I mean, depth first search everybody knows for decades, right? I mean, these are what we grew up with. And without knowing, or at least showing it to a larger audience what double depth first search is, how is it going to be, its power be used? Who knows where it can be used? Or people, have many, many very, very interesting and imaginative ways of changing things around and using it in different places. That has never happened. That was the reason to give this two talk sequence.
Any other questions? Let's send this to Karen.